history session this afternoon. Before we get started with our first speaker, I just want to say throughout, as I introduce the speakers, I'll be reading bios that were put together by Sylvia Nickerson. So I'd like to introduce our first speaker, Marcus Barnes, who earned his BSc from York University and his MSc in mathematics from Simon Fraser University under the guidance of Tom Archibald in 2007. In order to obtain this degree, he defended a thesis entitled John Charles Fields, A Sketch of His Life and Mathematical Work. We're grateful to have Marcus Barnes here today for expanding upon this research. So thank you very much. Marcus, please.
Great, thank you very much. So this is basically a recap of my master's thesis. Again, I want to thank Sylvia and the organizers for inviting me. Oh, louder? Yeah, okay, that's great. So just in the back, can you hear me better now? Thumbs up? Louder still? Okay. Okay, so anyways, here we see John Charles Fields, born 1863, 1932. So what I'm going to do today is start off with a little bit of a bit of a biographical sketch. The next speaker, Elaine, will expand on that and talk a little bit more about how the IMC came to Toronto, and then Dimitri will sort of contextualize what it was like in Toronto around 1924. On the second part of my talk, we'll actually look a little bit at Fields' mathematics, in particular his algebraic function theory work. And you'll see in the front here, there's actually a manuscript version of his book and the printed version. So just interesting stuff there. So he was born on May 14th, 1863 in Hamilton, which is southwest of Toronto, just on the corner of Lake Ontario. And he was the son of a leather shop operator, J.C. Fields, and his wife, Harriet Bowes. And there you can see just an advert that appeared in the local newspaper, the Hamilton Spectator, back in 1861, so just before Fields was born. Fields, there were multiple children born to the family, but only one sister and brother survived, and Fields was the third sibling. And he attended Hamilton Collegiate, and that's really where his mathematical talent was recognized and cultivated. So it was really formative. And Hamilton Collegiate, the building is still in existence. So if you're ever out in Hamilton, you can actually see where he was doing high school math. So he did very well at Hamilton Collegiate. He won some awards, and that brought him to the University of Toronto in 1880, where he specialized in mathematics. So at that time in Canada, there wasn't that many universities, but a BA degree sort of consisted of, you'd look at Euclid's elements, algebra to the binomial theorem. So like very basic stuff now, trigonometry, right? Some mathematical physics, so mechanics and hydrostatics. And then as an honor student, though, you could take more advanced courses. So again, this sounds a little bit weird, but conic sections, differential integral calculus, and differential equations. And then various topics in applied mathematics. And Fields actually did very well in his undergraduate career, and he won a gold medal upon graduating in 1884 on a BA. And then, the natural question for someone who's really bright in mathematics, and what are you going to do? Does he go back to Hamilton to take up his family business, or where does he go? At this time, there's no PhD programs in mathematics in Canada. So the options were either go to the few institutions in the US or go to Europe. And what Fields chose to do was go to the newly established Johns Hopkins University. And the math department for the university was established in 1876. And the mathematics department was put together by J.J. Sylvester, a notable mathematician. In particular, I'll probably say more about this in the panel, but I think Sylvester had a formative view on how he approached things. The British mathematicians liked to algebraize things, and so I think this influence, sure, the algebraization poured over into Field's work. So from the start, at that faculty, or at Johns Hopkins, the research productivity was of high importance. So this was different than a lot of other places in North America where it was just mostly teaching, right? But at Johns Hopkins, it was created as a graduate school. Research was always viewed, was highly regarded. So as I mentioned, even though Sylvester left before Fields attended Johns Hopkins, this would have a profound influence on his early mathematical work, and in particular the symbolic method in analysis. So, well, he and which he used to did his PhD thesis in. So at Hopkins, Fields took courses on algebraic theory of functions, linear differential equations, elliptic and abelian functions, among many other topics. And he also participated in several topic seminars, and most of the courses that Fields took were either taught by William Story or Thomas Craig. And in 1887, Fields received his PhD with a thesis entitled Symbolic Finite Solutions by Definite Integrals of this equation here. And so let's just talk a little bit about what he did in his thesis. It's similar to certain Riccati equations. And Riccati was an Italian nobleman and mathematician, and he studied certain second order differential equations of that form where A and B are constant. And in generalized form, it's written below, like that. And so again, using symbolic methods, Fields was able to give the following general solution. Case one, when m equals negative 9i over 3i plus 1, here's the solution, and the second case as well. In the second portion of this thesis, Fields also gives a generalization of a result of Edward Kummer and Spitzer for the solution for the solution of this equation here. By definite integrals. Furthermore, by using some of the methods from the first part of his thesis, he's able to give a particular solutions indefinite integrals for given values of m. So for example, Fields shows that this equation here has a solution given in this form, where m is any positive quantity greater than n. So after getting his PhD, Fields became a fellow at Hopkins. So it's sort of like a postdoc, I guess. And this entitled a certain amount of undergraduate teaching until 1889. Afterwards, he took up a post at Allegheny College in Pennsylvania, again, mostly teaching. And during this time, he did publish, including some proofs of the fundamental theorem of algebra, the elliptic function addition theorem, as well as some papers on number theory and some further work on differential coefficients, again, using a symbolic method. And many of these papers appeared in the American Journal of Mathematics, which had just started around that time. So in 1892, Fields resigned from Allegheny, and the reason was that both his parents passed away, and he came into a modest inheritance. And so he decided to use this money to continue his mathematical studies in Europe. So in the standard obituary by J.L. Synge, he states that Fields spent 5 years in Paris and 5 years in Berlin. I only know of documentary evidence for Fields' stay in Germany. Elaine might be able to speak about Paris. But we know, like, he enrolled in Göttingen in November 1894, and he had the opportunity to attend lectures by Felix Klein on number theory, as well as an introductory course on the theory of functions of a complex variable offered by Ritter. And he then stayed in Göttingen until, well, he stayed there until 1895, at which point he traveled to Berlin. And Berlin was a natural choice for Fields, given his early interest in linear differential equations and the fact that Lazar Fuchs and George Frobenius were there. And so during his Europe stay, he took a lot of notebooks of the courses that he attended. So there's courses by Frobenius, two on number theory, one on analytic geometry, and two on algebraic equations. By Fuchs, 9 courses, including the theory of hyperelliptic and abelian functions, and also some topics in differential equations. Kurt Hensel, 6 courses, including algebraic functions of 1 and 2 variables, and a course on abelian integrals, and a course on number theory. From Schwartz, he took quite a few. Topics included elliptic functions, variational calculus, theory of functions of one complex variable, synthetic projective geometry, number theory, and integral calculus. So you can see who's very busy. Some of the notebooks may have actually been copies of other students attending lectures. And well, like it goes on. And what's really interesting is that these notebooks are at the Fisher Rare Books Library in the University of Toronto Archives, so you can have a look. So Hattner, there's a course on definite integrals and Fourier series, and some courses by Knobloch on curves and surfaces, and Steinitz on Cantor's set theory. And in addition, and these are the ones which were likely copies, were almost the entire lectures by Max Planck, which would evolve into his famous course on theoretical physics, 2 courses in organic chemistry, and 1 on the history of philosophy. And this is a picture from one of those notebooks, and you can see the students using their imagination. So these are branch points, and he's turned it into a bug. And here's another image where again they're doing stuff here, and then those are the Berlin subway stops. So he's just I guess getting bored in lecture and filling that in. So there's some nice little fun things that you can find in the notebooks, and they all mostly, the handwriting is very similar to that. This is Fields' leaving certificate that just sort of acknowledged what he was doing. And so from this time, like from 1894 to 1900, there's no published papers per se, though he continued to do research. And he presented a talk at the American Mathematical Society held in Toronto in 1897, and on the reduction of a general abelian integral. And then he published this paper in 1901. And it's, given how busy he seemed to be, it's not surprising that he didn't write any papers. But it's also interesting from, I think, the panel the other day, in terms of getting a wide variety of information and attending to as much as he wanted to. So he was trying to learn as much as he could. In 1902, Fields took up a position as special lecturer at the University of Toronto. And at that time, the department had about 5 staff, including Fields. And then by 1905, he had gained a regular position as associate professor. And then he later became a professor in 1914 and research professor in 1923. And among some of the honors for a lot of his work that he did, he was elected to the Royal Society of Canada in 1909 and to the Royal Society of London in 1913. So on a local level here in Toronto, he was very active in the life of the university, often giving talks to the mathematics and physics student club. And he also lobbied the Ontario legislature for monetary support for scientific research being carried out at the university. And Elaine and Dimitri will talk a little bit more about that. And he was also gaining experience in event organization, scientific event organization. So he was the president of the Royal Canadian Institute also from 1919 to 1925. And at the international level, Fields he loved traveling. So he was always traveling and meeting people whenever he had the opportunity. And so Fields was the vice president of both the British Association for the Advancement of Science in 1924 and the American Association for the Advancement of Science, Section A in 1924. And of course, he's well known for the event that we're celebrating today. And unfortunately, it was during the cross-country trip that his health started to deteriorate. So it's probably better that the organizers didn't train us out to Victoria, because we wouldn't want any of us to get sick. So now I'm going to talk a little bit more about the theory of Field's theory of algebraic functions. So at the turn of the 20th century, there were several approaches to the theory, and they were usually categorized either as transcendental, geometric, or arithmetic. So Field's approach seems to be an outgrowth of Hensel's push for a purely algebraic approach to the theory of algebraic functions. However, Field's approach, contrary to what was presented by Hansel and Landsberg, and they also published something similar in 1904, seems to have retained some of the Weierstrassian function theoretical methods, in that he avoids the use of Riemann surfaces and the theory of divisors entirely. So again, just to sort of reemphasize, like at that time, they didn't really know what was going on. They were still sort of feeling out the field. They didn't quite understand how to approach it, right? So it's not until later, maybe until the 1960s, that people really started to have a really good intuition about what was going on, and even the best ways of approaching it. And of interesting note is that Fields really thought that pure research was really important. And so I think part of his push to create his own theory was to be a theory builder, because he felt that that was the highest academic or intellectual pursuit or contribution you can make. So he has an article where he actually goes through saying, okay, you can be an expositor, you can be a teacher, you can maybe be a problem type person, but he really thought highly of theory builders. And so his primary goal was to study rational functions subject to the condition defined by an algebraic function, f(x) of y equals to 0. And we would now describe those as rational functions on a variety. So Field's theory is built up on this concept that he calls order of coincidence. So the order of coincidence at a point is a rational function, h(x) of y, with respect to a branch, y minus p equals 0, which is the smallest exponent of the series expansion for h at p. So here's an example. So consider this rational function, y squared plus 2, subject to f, this cubic. Then the order of coincidence can be found by substituting y equals pi into h, and this results in this expression when we expand. And then so if you look at the highest order of respect to the branch y minus pi, it's 2/3. So the order of coincidence here is 2/3. So using this machinery, he's able to build up a theory that recovers some core results of algebraic function theory, like the Riemann-Roch theorem. And so here's a version of the Riemann-Roch theorem that Fields gives. So again, some terminology that Fields used in his book that you'll see up there. So a curve C is said to be a joint to C prime is said to be a joint to a curve C when multiple points on C are ordinary or cusps, or if C prime has a point of multiplicity of order k minus 1 at every multiple point of C of order k. So a bit of a mouthful. So that's what a joint curve is. And then he also has this concept of the strength of a set of multiple points. So given a curve f equals 0 of order n, the strength of a set of q multiple points used in determining an adjoint curve of degree n minus 3 is defined to be the number of q conditions to which the coefficients of the general adjoint curve of degree n minus 3 must be subject in order that it may pass through these q points. So an algebraic function of this form can be factored into a product of row irreducible factors. And in stating the Riemann-Roch theorem, Field uses the following notations. He indicates the poles as C sub I, and the first order by C sub I to the power -1, and uses the term coincidences to indicate singularities such as ECIs. And then this is the theorem, the version that Fields gives in his memoir that you'll see there. So the Riemann-Roch. So the most general rational function of xy, whose infinities are included under a certain set of q infinities, C sub 1, right, depends upon large Q minus Q plus P arbitrary constants where Q is the strength of the set of Q coincidences C1 through CQ. So the reception of Field's work. So from the mathematical point of view, George Landsberg, who had also taken work to find a new algebraic approach, algebraic proofs of the Riemann-Roch theorem, and reviewed in the Urbach, which is sort of like the math signet at the turn of the century. So it's a reviewing and abstracting journal. He said he had reservations about Field's earlier works on algebraic function theory, and particularly with regards to the simplifying assumptions that were made based on geometric arguments. That is, Field's approach was not algebraic enough for Landsberg. And then, given that much of Field's later writings were reworkings of various parts of his 1906 monograph, we can surmise that the reception of his monograph was lukewarm, at least from the international mathematical community. However, it did, oh, sorry, I'll say that in a bit. So here's another reworking, right? So in 1910, he published his paper, The Complementary Theorem, in the American Journal of Mathematics. And Faber from the University of Königsberg, in his review of the paper in the Urbach, wrote, this paper purports to give a proof of the so-called Weierstrass preparation theorem, which the author gave in the 11th chapter of his theory of algebraic functions by a shorter or simpler one. However, the proof still seems to me long and hard to understand. In another review of a paper by Fields entitled Direct Derivation of the Complementary Theorem from the Elementary Properties of Rational Functions, which he published in the Proceedings of the 5th International Congress of Mathematicians, Professor Lamp from Berlin quoting Fields' own introduction to the paper in the Philosophical Transactions, where Fields claims to have achieved simplification, that perhaps Fields could try for even more simplification. So, feedback, I think we're all somewhat used to. So, so Fields' research productivity started to subside as he spent more and more time as a scientific organizer in the 1920s. And then, of course, after the 1924 Congress, his health began to deteriorate. So Fields unfortunately died on August 9th, 1932, apparently from a stroke. He's buried in Hamilton Cemetery, which overlooks the western end of Lake Ontario. It's just a very modest stone set in the ground, and just basic information. So, however, he left in a small estate, a large part of which would be used towards, that would become the International Medals in Mathematics that he was in the process of organizing. And he also left his brother a small annuity and his maid, a widow, a small pension as long as she remained unmarried as well. So let's just talk a little bit about the impacts of Fields' mathematical work. I think that's fair to say. So exactly who read his work? I think his student, he had a student, Samuel Beattie, who was very formative in the early life of the mathematics department here at U of T. Bliss mentions his book, but it never really caught on, right? Like other approaches just were more natural for more people, and it just seemed to get results quicker. But what it did do was it helped establish him as a scientific authority here in Canada, where the society was very agrarian. There wasn't really a lot of respect for higher order thinking. So it really helped establish his reputation. So it gave him street cred, as they say, and so this helped him to get elected to the Royal Society and other societies and academies. And even though it was old-fashioned in the sense that it didn't afford easy generalization, I mean, it would be assumed by machinery offered by modern abstract algebra. So the ultimate influence of his work is small mathematically, like in terms of actual continuation of the work, maybe a little bit expressed through his student. but like I said, it legitimized him as a scientific authority. This played a key role in his push, along with others, to get governmental support for scientific research. Elaine's going to be speaking a little bit about this. And so it was basically that helped him, along with others, helped create the infrastructure that we all take advantage today, like the Fields Institute, the university, mathematics departments where you can get a PhD, things like that, right? And so even Beatty, he says, by his insistence on the value of research. So again, this is something that was very top of mind in research. Fields wrote about it quite a bit. He perhaps did the most to advance the cause of mathematics in Canada, at least up to that time. Thank you very much for your attention.